Can you hear me? Okay.
Yeah, yes, I can. And it says that it's recording. So,
Yeah.
okay.
Yeah. And yeah, this is Santosh. So I'm reaching out to you as part of my master's project that is on the bioreactors and predictive modeling technologies in recent years or in recent decades. So as part of this interview, I'm looking to get your field expertise on the bioreactors in the production of biopharmaceuticals. So this I'm going to record this audio and so whatever the fine discussions from this, I'll be using it only for the academic purposes, and
Okay.
we won't be sharing any personal information to anyone.
Okay.
So with that, can you introduce yourself and your expertise, your experience in the biotechnology field?
Yeah, sure. Yeah, my name's Andrew Fjordless. My background is in chemical engineering. I have did my undergraduate work in chemical engineering and also my graduate work. Um, and let's see, the after my undergraduate, I went and worked in industry for about 8 years. And I was at Pfizer and then Genzyme. Um, and then I went to graduate school at Tufts University. And I would say focused on the more computational aspects of chemical engineering. So it was a lot of statistical modeling, um, design of experiment, and mechanistic modeling. Um, and then, yeah, and then after grad school, I started at Takeda, where I'm in a technology excellence position. So it's basically digital and data analytics, along with innovation with respect to our biologics products.
That's great. Yeah, that's a very impressive background. Um, yeah, so going into the topics, maybe we can just start with your uh, idea of bioreactors in the commercial scale. What are general performance issues that can happen with the commercial productions? You yeah, anything that you can share?
Okay. Well, I mean, I think it obviously depends on the type of bioreaction, um, the type of cells that you're using. So, I mean, I guess if you were to, break it into categories, you've got your batch and fed batch, um, and then the more continuous bioreactors, whether it be like a chemostat or um, a perfusion type
Yeah.
um, bioreactor. Um, so, I think
Yeah, maybe
again, yeah, it was
automation
just
methods or something.
automate. Yeah, so no, what I was going to say is that I think it really comes down to like the type of product that you're producing, and what I've read in recent literature is that there's a push to try and go towards the more continuous um,
Yeah.
types of bioreactions. So whether it be the chemostat um, uh, or perfusion based, and with the perfusion, you've got that cell retention mechanism, whereas with the chemostat, you have cells that are exiting the bioreactor. in the harvest stream. And so, with those, you're able to operate for longer periods of time, and you can have a better control on um, the
The critical
sorry.
parameters.
Well, yeah, I'm having a hard time finding the word. Um, the the composition of what's
Okay.
in the bioreactor. So yeah, you can
Okay.
control uh, the metabolites and that sort of thing um, more easily than you can um, in a batch or fed batch um, bioreactor.
Okay. Yeah, that's good to know.
And I would say with the fed batch, I mean, you could potentially, because you are feeding, and typically, well, again, it depends on how the process was developed. You might have you add media once halfway through, and then there are others where you're adding it each day. Um, but if there's a way that you can add media slowly to try and control the glucose at a um, certain value to try and optimize your titer. Um, I mean, that's one way. That's one way of like operating a fed batch. And I've
Yeah.
actually seen with the fed batch like different different feeding strategies during the um, during the bioreaction, where you might add um, more glucose in the beginning and then kind of taper the glucose concentration down throughout the bioreaction, and that can have an effect on the amount of titer that you're producing, and certain
Mm.
glycosylation profiles, and that sort of thing. So it that um, there are a lot of different ways to do it, and then I also think that it depends. I think a big part of it depends on um, the company and what they're comfortable doing. So if you have a company that has a bunch of products and most of them are, batch or fed batch, they're probably going to stick with that method of bioreactor because um, they have expertise in it, and to like try and switch to, a perfusion based system um, is, I suppose, a risk. Um,
Yeah, I agree.
so yeah, so there's also that.
Yeah. Okay. Yeah. Thanks for that. Mm, so the next question I have is around, uh, yeah, so the technology we use on the bioreactors, like the PAT, process analytical technology, and like if using this technology, like is it worth implementing these technologies, especially with the type of regulations company organizations can face by FDA audits? Is it going to be advantageous, or like do you think uh, is there any like uses or no uses?
So I think that there are a lot of uses, and I think it's something that we should be doing more of. I mean, if you think about the cost of um, a some sort of spectroscopy instrument, whether it be NIR, Raman, UV, the cost of the instrument and putting a probe in a bioreactor is not it's not a lot of money. And then once it's in there, you can start collecting data. Um, but you also I mean I think there needs to be the adoption of this type of technology at at the development scale as well, because that's where you're going to be looking at a large design space,
Okay.
and able to, you're varying a lot of different parameters, and it's also probably where you're going to create, you know, some of the chemometric models, and that sort of thing, so that if you have a probe in a bioreactor, you could use it. You could use the spectra to then, estimate uh, some of the different metabolite concentrations and that sort of thing. And then once you're doing that, um, if you're in a perfusion-based system or a continuous system, you should then theoretically be able to monitor monitor those metabolites, and if you need to adjust um, the amount of a certain metabolite in the media, be able to start doing that in real time, so that you keep the composition of the bioreactor sort of at an optimum. Um, and then also, the same thing for the fed batch systems. Like I was saying before,
Mm.
it may be that you follow some sort of time varying profile for the glucose concentration, or the in order to maximize titer, or um, hit I don't know, hit I target like a certain glycosylation profile, or something like that, because that's where the glycosylation and that sort of thing is. All of that is taking place in the bioreactor. And so if there's a
Yeah.
way that you can um, control that based on, controlling the metabolites, or other media components, that then, you have the potential to then, really optimize your process. And yeah,
Okay.
I,
Yeah.
so I so yeah, I do think that it play that there is a part for it, and that we need to um, start thinking about it. Um,
Yeah.
and I mean, I won't say the product names, but in the chemostat process, we have a conductance probe that monitors the biomass concentration. And so, you can then operate your bioreactor to sort of maintain a certain biomass concentration, so that it isn't fluctuating during the bioreaction bio
Yeah.
yeah
Okay.
during the bioreactor. And then uh, so this isn't a, a bioreactor example, but um, you know, starting, and I guess this is probably more used in like the fine chemical industry and stuff like that, but using these spectroscopic techniques to um, monitor a reaction or something like that, and then you would operate your process to the reaction endpoint, rather than um, operating it for a certain amount of time. Um, and so there's an example in at Takeda where, in one of the downstream processes, they're using NIR to monitor one of the process steps to make sure that it going to completion rather than just running it for a certain amount of time. And so I think it's projects like that that are going to show um, the power of these
Okay.
PAT techniques, and once the company becomes comfortable with them and they've had some success, um, with the regulatory filings and working on these types of projects with the FDA and getting the FDA to buy into them, then I do think that we'll start to see more of them. And
Okay. Yeah.
yeah, but as an industry, I think that's the direction that we need to go, in, because um, it will reduce waste, it will increase productivity, um, and
Right.
yeah.
Yeah. Okay. Yeah. That makes sense. See, as we are on the spectroscopy like topic, I just want to ask one like follow-up question. Uh, so in terms of the bioreactors and like you using these spectroscopy technologies, is it going to be like real-time measurements, like supporting the real-time decisions, or like do they need to be some kind of QC lab-related equipments that takes time to provide as a results? Like,
Yeah, so I mean, there would be, I, what I think you would end up having is, an initial phase where you're developing, the chemometric model. So you're feeding all of the spectra into a model, and then using that model to make a prediction about, a concentration in your bioreactor. So in the beginning, you're going to have to be collecting spectral data from, you know, defined experiments that are coming from the lab, um, in order to create that prediction model.
okay,
And then once you have that, you would take it to, your production bioreactor, and you could you'd probably just start monitoring the process, just collecting spectra and
okay, got it. Yep.
calculate or predicting whatever concentration it is, and then pulling samples and confirming that um, what you're predicting is in fact what is happening in the bioreactor. Um, and then once you feel comfortable with that, you're going to have to go through, model validation and life cycle management of the model and that sort of thing. But there'll probably be some tweaks that you need to make to the model with the production data. But once you have once you feel confident in the predictions that model is making, yeah, you could turn it, you could put it online, and then you could start controlling, the concentrations of components in the media, that you're feeding in as the bioreaction progresses.
Okay, yeah, that's perfect.
Yeah.
Um, yeah, so yeah, now I think we can make transition onto the data like analytics, because in as part of the spectra survey you mentioned like we need to make some kind of predictive models so that we can predict like critical process attributes or critical quality attributes. So not only on the spectroscopy but like in general, when we are operating commercial bioreactors there is like a lot of data uh, being generated, uh, like in terms of raw materials or inline process data, like temperature, pressure, and like many other information. So, what are the different like data like analytical methods, uh, like PCA, principal component analysis, or partially like projections to latent structures, and then like anything else, like do you think are like being used predominantly in the industry?
Yeah. Um, so I think this gets broken down kind of into maybe two or three bins, where you
Yeah.
would have your statistical models, your mechanistic models, and then, a hybrid model where you're um,
Okay. Yeah.
combining mechanistic aspects and statistical aspects. Um, Obviously the mechanistic um, modeling is difficult in with respect to, all of the different interactions that you have going on um, within the bioreactor.
Mhm.
Um, and there are a lot of tools that can be used to help determine the kinetics or the important kinetics that are going on within the bioreactor, using metabolic flux analysis or dynamic metabolic flux analysis, to sort of get an understanding of the kinetics. So, I mean, you're essentially starting with like um, uh, the network pathway of the cell and sort of how it expresses different things, based on your understanding of the cell and how you've engineered the cell to produce your protein of interest. Um, and then um, within the mechanistic part, you know, the using the metabolic flux analysis and that sort of thing, that's going to lead to like um, a structured model. You can also have unstructured models which use like simple Michaelis-Menten type kinetics, and you're um, not really too concerned about what's going on in the cell. You're only using like the external measurements of the so basically what's uh, in the bioreactor harvest material. So, it would be like glucose, glutamine, glutamate, lactate, and other impurities, and that sort of thing. And you can kind of create simpler models, but those are typically not as accurate. Um, and then there are, the more statistical techniques, or um, where, you're using PCA or PLS to create kind of like a real-time monitoring um, model. So you're using like historical data, and
Mm.
then essentially um, picking good batches and creating uh, uh, like a PLS model, and then
Yeah.
comparing the the real-time data from the process, and bringing that in, and looking for, I mean, that's essentially looking for differences in the covariance
Right.
structure, the underlying covariance structure. And if it starts to deviate, then, you can intervene more quickly than if you were like trying to look at everything in a univariate sense. Um, and then you've got the hybrid models where you're kind of bringing together some of the mechanistic um, aspects, um, and then using either classical statistical or I guess more um, some of the machine learning algorithms to try and um, use your data to look for
Okay. Yep.
correlations that way. And the thing with the machine learning techniques is now, with like decision trees and random forests and even with like the neural networks and that sort of thing, you can get you can you get they can take into account nonlinearities in the system, and because these are typically batch systems, they're highly nonlinear.
Mm.
So you can exploit those nonlinearities using some of these newer techniques.
Oh, okay. Yeah. That's very
But
interesting.
yeah, but again, I think like in order to exploit them, you do need um, a lot of this a lot of the data needs to be generated um, at the lab scale because again, you need a large design space. You need to be able to vary um, different. Um, you need to be able to vary your inputs um,
Hmm.
so that you can um, get a sense of what's going on within the design space because at the commercial scale we operate in such a tight control space that it's more difficult um,
Hmm.
to I guess find a signal um, that that actually means something.
Yeah. Okay. Yeah, I think yeah, that's a lot of information. It also like answers like part of my like final question. So
Okay.
yeah, like summarizing all the information, like all the like we talked about different analytical methods and like different data analytic methods. So like uh, maybe in a like quick few sentences, like what do you envision a like an ideal bioreactor system that is like with the highest performance, like what kind of technologies you would use, what kind of analytical methods you would use, uh, yeah, maybe, yeah, what are your thoughts?
um, well, I mean, if it were a
In a hypothetical like
yeah,
imagination.
no, I mean, yeah, there are a lot of ways that you could go. I mean, you could go to the extreme and say like, oh, well, I'm going to have automatic sampling with like mass spectroscopy and, be able to measure every single little thing um and try and control that way. But I don't think, we're going to go to that extreme at the commercial scale. I think having um inline analyzers so that you can um, follow the metabolite concentrations during the bioreaction,
Mm-hmm.
um, and then uh, and then potentially using that. I mean, you can then create soft sensor type um,
Right. Okay.
approaches to try and estimate your product titer. I don't know, but the other thing is you could also try and create a spectroscopic model to monitor titer in the bioreactor as well. Um, so I don't know like if there's an ideal way to do it,
Mm-hmm.
um, but I do think that we need to start
Yeah,
getting a
at
better
least
under
with these, right.
yeah, I was just going to say getting a better understanding of these technologies and uh, building a certain comfort level um, around them, and then bringing them into the process to provide provide information that can be, exploited during the course of the bioreaction, to help with, tighter control, and a robust, more robust processes.
Right. Okay. Yeah, I think everything is like makes sense. And yeah, I think that's all the questions I have, and it's I would say it's very valuable information, especially for my project. I want to
Okay.
thank you so much for your time.
Yeah, no problem.
Yeah, with this I'll just stop the recording.
Okay.